So Faraday's law, the integral form, and some sample problems. Let's state the Faraday's law here. Well, let's start with this. Oh, look at that. We still have this color. Let's change this out to black. So Faraday's law in this form first, because this kind of, I think, if you keep this in mind here, d phi dt, then I think it's good to keep this always in front of you, because this really tells you that if you have a changing magnetic flux through a loop, then you end up with a voltage in that loop, and therefore the charges will flow. That's the concept. And then the more convoluted, if you will, equation that allows you to do some things that this equation wouldn't allow you to do is this one. That is that E dot dl along the edge of a surface is equal to minus d dt b dot dA, where you calculate the flux of the magnetic field through the surface. Let me state this stuff here. This is flux through surface S, and then this is the line integral along the edge, of surface S. All right, and so the picture one more time looks like this. Here's your loop. Magnetic field points through this. So here's B, and then when you integrate the flux, the magnetic field, you integrate it through the surface. But when you integrate, when you do the line integral of the electric field, then you integrate that along the edge of that surface. Get up all of these little dLs, and there's an electric field present here. So there's a changing magnetic field, then you have a changing electric field present in this space, and maybe I should add that to the picture. So if you have a magnetic field at points like this, and this magnetic field is changing with time, then what you get out of it is an electric field that is present. You have an electric field that is present around it, and I really should draw these little fields, like these little vectors like this, where this thing curls around. But so you have a curling electric field. And as a side note, before we start solving the problems, the curl of the electric field is in fact equal to minus dB dt, and that's the same equation. This is the same equation as this one here. It's just that this one is the integral version and this is the derivative version. So from this equation, actually, it's a little easier to figure out the direction of the electric field. It's assuming you know how the magnetic field is changing. But anyways, so let's go ahead and look at some sample problems now that we have the equations. And I'm looking at page 984 in your textbooks, number, what am I doing? Number 36, I think, is what I'm doing. Number 36. So you can look this problem up and you can read the text, and in the meantime, and you can try to solve it without looking at how I'm going to do it. And then once you get stuck, or once you finish the problem, you should go back and look at how I did it. Make sure that you got it correctly. Or to figure out what you didn't understand. So number 36, what we have is a ring that is placed in a magnetic field. Let's draw a picture here. What we have is a ring. It's like this, and then the A vector points to the right. The A vector points like this, 90 degrees, and then we have a magnetic field that, well, what we have is a magnet. So we have a magnet that sits here. Here's the North Pole, and then there's a magnet that sits here. Here's the South Pole. And we have a magnetic field pointing from here to here, from here to here. So there's a magnetic field here. And of course, that magnetic field points through the loop of the wire here. What they tell us, though, is they give us the diameter of the ring. So let's state all of the knowns. What we have is the diameter of the ring. Therefore, we have the radius. Radius is 2.25 centimeters, so 0.0 0.25 of a meter. That will allow us to calculate the area A. So we can calculate A. Let's do that. So it's 2 times 10 to the minus third. So it's 0.002 meters squared, rounded. And then I have magnetic field is changing. It starts at 1.12. So the initial magnetic field, I'm going to put here, the initial magnetic field is 1.12 Teslas, but it changes. And it changes at the rate of 0.25 Teslas per second. So in other words, what I can write is that the magnetic field as a function of time equals 1.12 minus, and then it changes at the following rate, 0.25 Teslas per second. So times t, 0.25 times t. All right, so this is the expression for the magnetic field as a function of time. What's happening here is that we take these magnets and we pull them back. We pull this magnet back, we pull this magnet away, and then the magnetic field, the magnitude of the magnetic field is decreasing. The problem tells us how that thing is decreasing. So what is the magnitude of the electric field induced in the ring? All right, so in the first place, because we have a changing magnetic field, we will have a current flowing through this loop. And we haven't played with determining the direction of the current yet. That's going to come in Lenz's law, but let's just say that we know how to do it. Let's say that the current itself is going to flow. So let's say that the current itself flows in this direction. This is I, and that means that there must be some kind of, if this is how the charges are to flow, because you have charges in this loop here. If this is how the charges are to flow, then that means that there must be an electric field pointing more or less in this direction, pushing them to go. So you will have an electric field here that points along this loop. Here's the electric field E. It doesn't actually have to be even necessarily tangent to this loop, but it has to be there. It has to be present along this loop so that the charges can actually flow. But we will just simplify it and draw it as if it was tangent to that. So here's the electric field present everywhere. And of course, if you move away from this wire, you will still have electric field, you know, somewhere out here, you will still have the electric field that loops around. And, but let's not add all of that into the picture, will look convoluted. If you move somewhere out here, you will still have the electric field that loops around. But let's also get rid of it. In other words, all of this space here is going to be filled with an electric field that curls, that curves and loops. You're going to have a looping electric field all over the place here. It doesn't have to be necessarily perfectly circular, but there's going to be an electric field that is going to loop everywhere here. And it has to be so, because as soon as you place a metal wire in this that has a shape of a loop, charges will flow. So there must be some kind of a looping electric field here that forces these charges and loops to flow. So anyway, so this is what we have for the picture. And now the question is, what is the magnitude of the electric field induced in a ring? So we're looking for this electric field E. The unknown is, this is one of our unknowns. What is the electric field here? So let's bring out the big equation and let's do that part. This is part A, by the way, finding the electric field. But let's do this. E dot dl over the surface of that surface, since I'm going to indicate that this is my surface, equals on the right hand side I have minus d e, and then I have b dot a. All right, so let's start with which side? Let's start with the left hand side. You wouldn't necessarily know it for sure, but take it from me that for all of the problems you're going to get with this specific equation, the electric field for you is going to be constant. And so you can pull this, and then the electric field is going to be parallel to the dl. Now in this specific case, it's not too difficult perhaps to see that that is so. I'm going to just state that, but just remember that if you are asked to solve one of these problems, you can use this, that the electric field is parallel to dl and that the electric field is constant. So E is constant, its magnitude is constant. The vector, it changes direction, but its magnitude is constant. So the left hand side, so maybe box this for yourself. if you get a problem where you have to use this equation, you can use these that the electric field is parallel to the element dl and that the electric field is constant. And so the left hand side just becomes E times dl integrated over the surface. The right hand side becomes minus d dt. And then what we have here is the magnetic field. Well, the magnetic field, well, okay, so first of all, the angle between B and A is 0, so B times dA, since theta between the two is 0 degrees, and that, in case you kind of got lost here, B dot dA is the same thing as, excuse me, B times dA times the cosine of the angle between them, but the cosine of the angle between them is just 0, and so that's 1, and so you end up with just B times dA. So this allows you to get rid of the vector notation. All right, let's go to the next step. Electric field times, well, what do you get if you integrate all of the little dLs along the loop here? Well, you just get the length of the loop. And that would be 2 pi times r. And I know the radius of this loop equals, and then you have minus d dt. It's really no. Anyways, the magnetic field B times the element dA, well, let's put this in. So what you end up with is the integral of 1.12 minus 0.25 t dA, and dA is just dA. What is that? Nothing here in this integral, nothing in here has anything to do with dA, so you can just pull this stuff out. And so let's take the next step. That is, I would have E times 2 pi r equals minus d dt. 1.12 minus 0.25 t, that comes out of the integral because there's just nothing relevant to dA in this expression, times the integral of dA over the surface S. And maybe I'll do this here. So the next step is the electric field. This should be times electric field times 2 pi r equals minus d dt of 1.12 minus 0.25 t multiplied by, well, what is the area of the surface that I'm considering? It's just pi r squared, and that will do for this part. So let's move this up. Then the electric field times 2 pi r equals minus d dt 1.12 times, I guess I could just, yeah, I know what this is. So the pi r squared, I already have this calculated. This is 0.002. So what I can do is I can, oh, I see, 0.002 meters squared. So what I'm going to do is times 0.002 minus 0.25 times 0.002 times t. And when I take the time derivative of this, one of these terms goes away, so I end up with electric field times 2 pi r equals minus go away. So what I have is 0.25 times 0.002. That's about it. I actually probably should have kept that. R squared. I don't think it really matters. It's kind of curious now what this would do. I don't think it would do much good to us, but let's write it this way. So electric field times 2 pi r equals 0.25. That's just the rate at which this field is dropping, times pi r squared. So I'm going to go back to this expression. So that allows me to cancel out pi, get rid of this r and that r, and I have that the electric field is 0.25 over 2 times r. So the magnitude of electric field depends on r, or it's 0.125 times R. If you were to graph this thing, what you would find out is that versus R, electric field versus R, that you end up with this thing just sort of doing that, right? Where the slope here is 0.125. So in other words, the electric field at the center, so let's maybe go back to the picture. The electric field at the center where R is 0 is 0. The electric field here is 0. And as you move farther out, the electric field increases and increases in its magnitude. It's sort of interesting. So if I were to draw this, what I would do is at the origin or at the center of the loop, the electric field is 0. And then as you move away from it, the electric field starts to pick up in value. So it becomes bigger and bigger and bigger, and it increases linearly. So I want to do another one. Yes, I do. And then this this thing loops around. Now at some point we find the size of our loop, right? So let's say our loop is actually somewhere, let's say our loop is here. So this thing loops around like this. So you're only really interested in this value of the electric field here. And that would be easy to do, easy to calculate. It's just 0.125 times R, where R was given to us as 0.025. And so whatever you get here is the answer to the solution to the problem, at least part A. But maybe just to complete this thing, so if I were to draw something like this here, I would have to draw this as, you know, the electric field here points like that, then it increases, and then it increases even more so here, and then at this point here I would have electric field at points like this, and here electric field points like that, and then the third one it increases even more so, and maybe I'll do one more. So here's the electric field increases with radius is bigger. And of course, if I move outside of the field, outside of the ring, you know, the electric field gets even bigger, right? So the electric field increases even more so outside, and here it would do something like this. And if you wanted to, you could do these, but I think we will live without that. That is, you could add electric field here as well, and that electric field is increasing as you move away. Anyways, there's the electric field in the space as the magnetic field is changing. So this was part A to the problem. Let's see what part B says. In which direction clockwise or okay, don't worry about part B because I haven't touched really yet how to handle the direction of the current. Although the way I drew it is correct. So the direction that I already gave you is the correct direction. I think it's easiest to determine the direction of the current and therefore the direction of the electric field by using Lenz's law. But Lenz's law is yet to come.